So the recording, I didn't record the first Zoom meeting. The Thursday Zoom meeting is now on the YouTube playlist at the end, or near the end. I just kind of added it on to the 381 playlist. So that's the meeting where I went over the test and all the questions on the test. So that's at the end of the 381 playlist. Sure. Just to make sure, we should watch 2 videos before every class. That's correct. Yeah, 2 videos before each class. So I'm trying to split up each lecture into chunks of 2. And so I probably should have written an announcement or something like that. But what I would have expected you to watch before today were the last video dealing with prime number stuff in chapter 4, and then the first video on induction. So just 2 by 2. Okay. So it's 12:30 and we can get more officially started. So the topics that I discussed in the, so we kind of missed a discussion last week, which we would have done on section 4.3. So I figure today I want to first answer any questions people have remaining on chapter 4. So 4.1 was modular arithmetic. And then 4.3 had a lot of stuff. It was GCD, LCM, the Euclidean algorithm, and the infinitude of primes. I think these are more or less the topics that I covered in the previous 2 lectures, and with a little bit spilling over onto today's video. So does anyone have any questions on these topics? Can we go over pairwise relatively prime? Yeah, definitely. So do you want me to just like write an example? Or do you have an example in mind? I can look for an example in the text. Yeah, okay. So let's look at problem 16. So it's going to determine whether, let's take a look at 25, 41, 49, and 64. Whether these are relatively prime. Okay, so as a first beginning step, can someone write down what it means for just 2 integers to be relatively prime? Yeah, 2 integers are relatively prime if their greatest common divisor is 1, which in particular means that they have no common factor. There's no number bigger than 1 that divides both of them. And if you write them all down in terms of prime factorizations, what that means is that 2 numbers are relatively prime if their prime factorizations are totally distinct, right? They share no primes when you break it down into the prime factorization. So essentially, when you extend the idea of pairwise pairwise relatively prime to collections of numbers, essentially you're comparing all of the different prime factorizations that appear in each. So the easiest way to do this is to just write out the prime factorizations of each number. So 25 is going to be 5 squared in its prime factorization. 41 is going to be prime. 41's prime. Is 41 prime? I think 41 is prime. We'd only need to check up to 7 squared. It's not divisible by 6, 5, 4, or 3, or 2, or 1. Okay, so 41 is prime. 49 is 7 squared, and 64 is 2 to the, what? 2 squared is 4, 2 cubed is 8, to the 5th. Okay, 41 is prime. Yes, thank you very much. So the point is here, to actually kind of naively check whether this collection is pairwise relatively prime, I need to form every single pair, right? I need to check, is 25 pairwise relative, or is 25 relatively prime to 41? Is 25 relatively prime to 49? Is 25 relatively prime to 64? And then is 41 relatively prime to 49? Is 41 relatively prime to 64? So there are a lot of pairs that I would have to check if I wanted to check each pair. But this actually tells me more. Here I see that the prime factorization of 25 only involves 5s, prime factorization of 41 only involves 41, 49 only involves 7s, and 64 only involves 2s. None of these share any prime factors. And not sharing any prime factors is the kind of core of what it means to be pairwise relatively prime. So since none of these numbers share any prime factors, this collection is pairwise relatively prime. Are odd squares always prime? Odd squares are never prime because they're squares. Right? If it's a square, so if, for instance, 49 is an odd square, but by the very virtue of it being a square, that means it can't be a prime number, right? A square is never prime because its prime factorization has 2 primes instead of just 1 or more. What is the purpose of knowing pairwise relatively prime? I think maybe I'm missing something. I mean, what to say? Pairwise relatively prime collections are interesting if you go further into number theory. In terms of this class, it just provides me some kind of fun number theoretic questions that I can ask you. So I don't know if that's a very satisfying answer, but and then question, are there only factors their roots? So here, once again, you're asking about 49. Yeah, I would say for the purpose of this class, there's not a big picture, but if you go on to do some number theoretic stuff, there is a reason to care about pairwise relatively prime collections of integers, yeah. But even if the only factors are their roots, like in the case of 49 or 25, neither of these are prime. Because to be a prime means that when you read out your prime factorization, there's only one prime counted once. Like 5 is a prime and 7 is a prime, but 7 times 7 is not a prime. Remember, right, a prime, P, has the property that the only divisors are 1 and itself, right? So 49 has a divisor of 7, which is neither 1 nor 49. Same with 25. Yeah, absolutely. Okay, so let's once again go over what the meaning or what the Euclidean algorithm relies on. So the Euclidean algorithm relies on the following point, is that if I have a number a, and I'm trying to write it with divisibility using, well, let me back up and do the following. Let's say that I am looking for the GCD of a pair of numbers, a and b, GCD of a and b. Here is the following point. Let's assume, without loss of generality, that a is greater than b. So the thing is, I can always, by the, I suppose, one of the fundamental theorems of divisibility, the divisibility theorem, I can always write a is equal to qb plus r with 0 less than or equal to r less than b, right? This is how we divide with remainder. Now, the point of the Euclidean algorithm is the following thing to note, that, so I'm interested in the GCD of A and B. In particular, the GCD of A and B, if something divides A and something divides B, so if, say, n divides A and n divides B, then n divides A minus QB, which means n divides R. So the GCD of A and B divides R. Moreover, any number which divides B and R must divide A. So what these two statements together tell us is that the GCD of A and B is equal to the GCD of B and R. I know that this is not exactly what you asked for, because what was asked for are examples, but is this clear or good? Okay, great. So the idea of the Euclidean algorithm is to reduce computations from the GCD of A and B to the GCD of B and R, which are one of the numbers is smaller. And then you keep on repeating it until they get so small that it's easy to compute. So with that in mind, let's now actually do some example. Let's do the following. Use the Euclidean algorithm to find, let's do, did I have you do problem 32 on the homework? I can't remember. Did I have you do problem 33? I just want to make a new example that you haven't done already on your homework. How about the GCD of 111 and 201? Have you done this one? 32 you've done? Have you done 111 and 201? Yeah, sure. That's true. There's no problem in doing it again. Okay, so if I'm trying to find the GCD of 111 and 201, the first thing that I'm going to do is I'm going to rewrite things with remainder. So the point is 201 is equal to 1 times 111 plus the remainder. And in this case, the remainder is going to be 90 plus 90. right? Zoom crashed. I don't have any more questions. Oh, yeah, sure. You too, Charlie. Okay, so this is the correct division algorithm expression of 201 divided by 111. And what we already know immediately is that the GCD of 201 and 211 is the same as the GCD of 111 and 90 by my previous argument, right? In other words, I'll make a little triangle, 201, 111, 90, and whatever the GCD of these two, it's the same as the GCD of these two. And now I keep on working. If I'm after the GCD of 111 and 90, I do the same thing. I write 111 as being equal to 1 times 90 plus 21. And now by the same story, GCD of 111 and 90 is equal to the GCD of 90 and 21. So I have another triangle of 111, 91, or 90, and 21. Whatever the GCD of these are, it's the same as the GCD of these two. And it's still not obvious to me what the GCD of these two are, so I now find what is the GCD of 90 and 21. Well, I once again write 90 as being equal to, let's see, 4 times 21. That'll get me 84 plus 6. Once again, this relationship says the GCD of 90 and 21 is the same as the GCD of 21 and 6. So I get yet another relationship that the GCD of 90 and 21 is the same as 21 and 6. And now the numbers are getting very small, so it's easier. GCD, so I'm interested in the GCD of 21 and 6. Once again, I write 21 is equal to 3 times 6 plus 3. Is that correct? Yes, that's correct. 18 plus 3. And so this equation expresses that the GCD of 21 and 6 is the same as the GCD of 6 and 3. Now, so our last triangle is 21, 6, and 3. And now we've gotten it so far down that we can just immediately compute what the GCD of 6 and 3 is. The greatest common divisor of 6 and 3 is just equal to 3. And I mean, you could even push the Euclidean algorithm even further until you hit a 0, right? I could say GCD of 6 and 3, then I write 6 is equal to 2 times 3 plus 0. And now what's the GCD of 3 and 0? GCD of 3 and 0 is 3, just like the GCD of 3 and 6 is 3. So my last kind of mini triangle is 6, 3, 0. And you can go back and check, right? GCD of 3 and 0 is 3. The GCD of 6 and 3 is also 3. Then you go back through and say, what is the greatest common divisor of 6 and 21? Well, 21 is divisible by 7 and 3, and 6 is divisible by 3. So the division here is just 3. Then I go back here. What is 21 divisible by versus what is 90 divisible? I mean, so we already have the answer. The answer is done. The GCD of this thing is 3.
Yes.
Right?
Yeah.
But what I'm kind of showing you is how you can go back and verify that in each step the GCD actually is 3 between each pair of numbers. 21 is equal to 7 times 3, whereas 90 is equal to 3 times 3 times 10 times 5 times 2. Once again, you can see what's the only thing that divides both of these numbers. It's exactly 3. Then you can go back through and, if this is 2 times 3 times 3 times 5, what is 111? 111 is, well, it's divisible by 3. And if we divide it by 3, what do we get? So we get 99. It's 99 plus 12, right? 3 times 99, or how does 3 go into 99? Man, this is going to be hard for me. But
What?
99, what's 99 divided by 3?
33.
33, right? 33, so it's like 37. 111 should be 37
37, yes.
times 3. 37 is prime, I think. So once again, you see what's the only common divisor between 3 times 37 and 2 times 3 times 3 times 5 is just 3.
3.
And then the last thing I check is this is 3 times 37, and 201 is,
67.
say that again?
67.
67 times 3?
Yes.
And is 67 prime? I think
Yes.
so. Yeah, 67 is
Yeah.
prime.
A
Right?
squared 64, right? Yeah.
Now, the point is the prime factorizations of things are usually kind of hard to compute, but these expressions, these divisibility expressions, are easier to compute,
Mm.
much easier. And so,
Now we see- yeah.
go on.
Every time we see this problem, now we just like, like set up like the steps like you are step in the blackboard, and we can find the GCD, right?
That's right. That's right.
You don't have to go over like to the zero when the example, like the test.
Once you found something where you know what the GCD is because you
Yeah.
can see it clearly, then that's fine.
Okay, there, right. Okay. Thank you.
Yeah, of course.
All right. Kind of the VIP class for me, right? I'm not...
Happy to provide it.
Thank you. Have a nice day.
You too.
Yeah. I'm done with the questions, so I'm going to, see more of your video. Okay.
No problem.
Yeah.
Have a nice, I don't know if it's afternoon or morning or evening.
It's
Are you back in China?
Oh, you know what? I think I have to go to China, but the many flights have been canceled, so
Yeah.
probably wait to wait to wait to May, I guess.
Oh, I see.
Yeah, I'm
Yeah,
finished
it's
this semester. I know that. Stay safe, sir.
and you stay safe as well. Yeah, it's
That the confirmed case is like growing up every day. It's like surge.
oh yeah, I've been watching what's going on in like New York, right? New
Yeah.
York and Italy and Spain. It's just uh unbelievable
Yeah.
how I don't know. And then I think well, I think things are going to be really bad in the southern states of the United States, like in Florida and Louisiana, where they had
Yeah,
really
yeah.
big spring breaks and they didn't do any
Like
social distancing.
I got the data from the website, and it's going worse and worse.
Yeah, I it's a dangerous time that we live in at the moment. So I hope you stay safe as
A
well.
tough time. Such a tough time for us. But thank you anyway. Thank you, sir.
Yeah, of course.
Yeah. Okay. See you.
So long.
Mhm.